Welcome to Lecture 6 on using inductive logic to correct for biases in reasoning. By the end of this lecture, you should be able to apply the principle of conservation of evidence and to be able to describe the following biases and how to correct for them in your own reasoning: the availability heuristic and confirmation bias, base rate neglect, and the conjunction fallacy. Let's begin. In previous lectures, we touched upon how biases have deranged our judgment in the domains of economics, politics, and philosophy. Now, to motivate this lecture, we'll consider the history of bias and bad judgment in the context of medicine. An extraordinary fact is that up until the early 20th century, that is, before the invention of vaccinations and the later adoption of evidence-based medicine, it is estimated that visiting a doctor actually lowered one's life expectancy. Humans in the medical profession throughout history and across cultures have presumably wanted to do good and genuinely believed that they did. How could they be so wrong? The pattern repeated across cultures and eras is that individuals with excessive confidence created bold theories, typically decrying their rivals as quacks, and then managed to successfully promote and ultimately spread these theories. Many such theories in medicine, psychology, politics, economics, philosophy, and so on have definitely done more harm than good, both for human understanding and indeed for human well-being. This has been a part of our history. To see what this confident, bad theorizing looks like, consider Galen, the famous 2nd century Roman physician, speaking on his science of medicine. It is I, and I alone, who has revealed the true path of medicine. All who drink of this treatment recover in a short time, except those whom it does not help, who all die. It is obvious, therefore, that it fails only in curable cases. In other words, if the patient is cured, this is evidence that the treatment works. If the patient dies, it means nothing. To take just a flake of 19th century American medicine, we can see that one school, Thomsonianism, was convinced that most all illness was due to an excess of cold in the body. Another school, that of Edwin Hartley Pratt, posited that all illness was due essentially to the rectum. And other notorious cures that were used broadly over the past centuries included bleeding, starvation, and in some cases strangulation. The image we saw earlier was of George Washington, who was severely bled before his death as an attempted treatment for his illness. Each of these cures is now recognized as clearly harmful. We can use the inductive logic of probability to understand why this sort of reasoning can't be right. One helpful principle in this regard is that of the conservation of evidence, which states that if observing some evident, or equivalently some proposition, E, increases the probability of a hypothesis, H, then observing the negation of that event or proposition, not E, must decrease the probability of H. For example, our hypothesis H might be that the treatment works, and our evidence E can be that the patient recovers, with not E being that the patient doesn't recover or dies. We can derive the principle of conservation of evidence with our familiar rules of probability. First, we begin by observing the logical equivalence of H and the disjunction of H and E, or H and not E. And then by applying the fact that logically equivalent propositions are equiprobable to get that the probability of H is equal to the probability of the aforementioned disjunction. And then, since H and E and H and not E are mutually exclusive propositions, we use finite additivity to find that the probability of their disjunction is equal to the sum of their probabilities. And finally, from the definition of conditional probability, we get the statement of the principle of conservation of evidence. The principle, however, involves applying or interpreting this theorem of the probability calculus to understanding the relationships between confirming and disconfirming evidence and the increase or decrease of our probability in a hypothesis. Let's see how that's done. Let's take our expression as we have unpacked it and say that the probability of H is some value. Perhaps we are confident that the treatment works, so the probability is above half. Now we want to consider the probability of the evidence, that is, of the patient getting better. We can represent that along the vertical axis, where the distance above our line gives us the probability of the patient recovering, the probability of E, and the distance downward gives us the probability of not E, the patient not recovering. And we can recall that the sum of those two distances need be 1, since the probability of E plus the probability of not E is equal to 1. Let's assume, for illustration, that the probability of the patient recovering and not recovering, that is E and not E, is simply 1/2. We can plug this into our expression and pull out the 1/2 to the front, observing that what this says then is that in this case, the probability of the hypothesis is simply equal to the average of the probability of the hypothesis given the evidence and the probability of the hypothesis given not the evidence. Returning to our interpretation, what this would mean is that if the patient were equally likely to recover and not recover after having been given the treatment, that our confidence in the treatment working should be equal to the average of our confidence that the treatment worked given that the patient recovered, and that the treatment works given that the patient doesn't recover. There's a nice geometric intuition for this, which is illustrated as follows. Consider the light blue square above our line. The width of this will correspond to our confidence if the patient recovers. That is to say, it corresponds to the probability that the treatment works given that the patient recovers upon receiving it. And the area below the line will correspond to our confidence that the treatment works given that the patient does not recover. Notice that one is greater than our current confidence that the treatment works, and the latter is lesser than our current confidence that the treatment works. Moreover, these two quantities need to average, as we had said, to our current confidence that the treatment works. That is to say, the amount that our confidence grows upon having observed that the treatment works should precisely equal the amount that our confidence shrinks upon seeing that the treatment doesn't work. This is our moral then. If observing some evidence increases the probability of the hypothesis, then observing the negation of that evidence must decrease the probability of that same hypothesis. Moreover, notice the balancing principle. The more confirming you think the evidence is, to return to our interpretation, the more confirming you think it is that the treatment works if the patient gets better, the more disconfirming you should think it is if the patient gets worse. Evidence must cut both ways. Any evidence that has the potential to confirm a hypothesis must also, in its absence, have the potential to disconfirm a hypothesis. But there's more to learn still. We chose areas for the reason that they have a meaningful interpretation. In particular, we can consider the height of the areas that we created. These correspond to the probability of the evidence, which we have initially stipulated was equiprobable. It was equally likely that the patient would recover or not recover. Width, as we said, corresponded to our confidence in the hypothesis, given that we observed the evidence. So the left hand portion of our sum is just the area that we see before us. And it's the sum of the areas that have to equal our current probability in the hypothesis. Similarly, the probability of not the evidence, as we said, was the distance below the line, and the width of that area is given by our confidence in the hypothesis, given that we did not observe the evidence, which produce our right-hand term of the sum as the product of those two. Let's assume now that the evidence is not equiprobable. We can say perhaps that we are confident that the patient will recover on receiving the treatment. So the probability of recovery is 3/4, and the probability of non-recovery or death is 1/4. Then we shift the vertical line to reflect this. Now, 3/4 of the probability of the evidence, right, is above our line and 1/4 below. Notice how this changes the areas that need to sum to the probability of our hypothesis. We plug in our numbers and observe that again, what we need is that the change in the probability in our hypothesis is conserved between observing the evidence or not the evidence, observing recovery or getting worse. Let's spell out what that means. We can define the probability of our hypothesis given the evidence in terms of the probability of the hypothesis before the evidence, probability of H, plus the change produced by observing the evidence, which will denote delta sub H given E. Similarly, we can define the probability of our hypothesis upon observing the negation of the evidence as equal to the probability of the hypothesis minus the change produced by not observing the evidence, not observing the patient get better, which will denote delta sub H given not E. So the first change corresponds to the area of increase past the current confidence in our hypothesis. And the second delta corresponds to the area of decrease downward upon observing not our evidence. And we can plug in these terms, which simplify with just a bit of algebra, multiplying both sides by 4, and then subtracting the probabilities of the hypothesis to get the two changes in terms of one another. Specifically, given that we stipulated that the probability of the evidence was 3/4 and the probability of the negation of the evidence was 1/4, the amount that observing the negation of the evidence, not E, should decrease our confidence in the hypothesis is 3 times as much as the amount that observing the evidence E should increase our hypothesis. That is, if the evidence is rare, observing its negation should be stronger evidence against our belief than observing the evidence is for our belief. Our moral is that the more probable the confirming event, the more severely its negation must decrease the probability of our hypothesis. To return to our interpretation, if patients tend to get better on their own without treatment, then the probability that the treatment works on observing the evidence should not go up very much. But if the patient gets worse, our probability that the treatment works should go down more dramatically. Notice that the converse also holds. The less probable the confirming event, the less severely its negation will decrease the probability in our hypothesis. So in our interpretation, if very few people recover at all on their own, then an individual recovering on having received the treatment is stronger evidence for the treatment working, and an individual not recovering on receiving the treatment is weaker evidence that the treatment doesn't work. We can consider examples of violations of the principle of conservation of evidence and see why it demonstrates that this sort of reasoning must be wrong. In Galen's case, the Roman physician, as we saw, he reasoned roughly that if the patient is cured, this was evidence that the treatment worked. But if the patient died, it meant nothing. The principle of conservation of evidence tells us that this is not possible. If, in fact, the patient recovering is evidence for the treatment working, the patient not recovering must be some evidence for the treatment not tending to work. Similarly, if a miracle happens tomorrow, someone might claim that this shows that their preferred deity is real. But if no miracle occurs tomorrow, they might say that it shows nothing. For the same reason, this cannot be right. If the miracle is positive evidence for a hypothesis, the absence of that miracle must be negative evidence. In the context of witch trials, we have a quote from Friedrich Spee von Langenfeld, an inquisitor who published the following claim in his Cautio Criminalis. If the witch has led an evil and improper life, she is guilty. That is, this is evidence that she is a witch. If she has led a good and proper life, this too is proof, for witches dissemble, that is, deceive, and try to appear especially virtuous. So whether the individual has led a good life or not a good life is positive evidence for there being a witch. It should be mathematically clear for us now why this sort of reasoning is not right. Indeed, it is logically impossible. Now let's consider some of the prominent biases that tend to derange our inductive reasoning, and some correctives for those biases. For our purposes here, we'll define a bias as a pattern of thinking that tends to lead to inaccurate beliefs, and a corrective as an action aimed at correcting for or compensating for that bias. There are indeed many biases that confound us. We'll focus on only particularly important biases for inductive reasoning. For our first two, the availability heuristic and confirmation bias, we can summarize their implications as follows. We move far too quickly from confusion and uncertainty to confident conclusions, without sufficiently reflecting. The availability heuristic is the tendency to judge the likelihood of an event or the probability of a hypothesis by how easily it comes to mind. This can be adaptive in some contexts. For example, consider the Paleolithic environment, in which one of our ancestors heard the proverbial rustling in the bushes, a sound that might indicate a predator or threat. They might quickly bring to mind a threat and respond as though there was in fact a predator. In this case, the probability estimate that they intuitively act on might in fact overestimate the likelihood of a predator. But that might in fact be the right response, to be in that case highly sensitive to the risk that might end one's life. However, this sort of quick reasoning, informed by how easily something comes to mind, is often bad when we want to accurately understand complex phenomena, rather than make snap judgments like the sort for which we were evolved. Some examples of the availability heuristic is that it is easier to recall plane crashes than safe flights, which can lead to an irrational fear of flying. Or it may be easier to recall cold spells and harder to recall gradual trends of warming, which can lead to ignoring phenomena like climate change. It can be easier to recall winning lottery tickets as opposed to the many losing ones that fall out of memory, which can lead to an overly optimistic perception of what the chances of winning are, and to the buying of more lottery tickets. As an illustration, we might think that the world is composed of a great deal of information. However, the information that we tend to use to inform our judgments are those that are recent, extreme, or negative, because of the psychological properties that these confer on our memories of events. The corrective to this bias is to keep score, or to find or create probability estimates for events. In this context, statistics and data are our friends, and we should be aware of selection biases in both our perception and also in data collection. There are many things that go by the name of confirmation bias. Here we'll use the following definition of the term. Confirmation bias, we will understand, is the tendency to seek, interpret, or recall data in a way that confirms one's current favored hypothesis. As an illustration, we might think of the world of facts and observe that confirmation bias is where we preferentially focus on the subset of the world of facts that confirm our current hypotheses or beliefs. This is a quote by Francis Bacon on the topic. The human understanding, when it has once adopted opinion, draws all things else to support and agree with it. And though there be a greater number and weight of instances to be found on the other side, yet these it either neglects or despises, or else by some distinction sets aside or rejects. The primary correctives to confirmation bias are first, to spend time considering alternative hypotheses to the ones we currently favor. As an exercise I strongly recommend, I suggest that when you wish to formulate hypotheses, take 5 minutes during which you will assume that your current favorite hypothesis is definitely false. Imagine that that's true. Now, list off as many other hypotheses as you can think of. Then the second corrective is to actively look for disconfirming and not just confirming evidence. Our minds, as we know, will tend automatically to try to find confirming evidence for what we believe. It's invaluable then to compensate for this by trying to find out how our beliefs might be wrong. As an example of considering alternative hypotheses, let's take an everyday case. Our friend Omid gave us a look like they were upset. The first hypothesis that may come to mind is that Omid was upset with us. But let's pause and imagine alternative hypotheses. Notice that the negation of our hypothesis, that Omid was upset, can be the disjunction of many hypotheses. For example, Omid was perhaps having a bad day, which is what explains the look. Or Omid was simply deep in thought, and they were not looking at us at all. It only appeared that way. Or perhaps Omid had to fart and was feeling some physical distress. What else? I'd invite you to consider for yourself alternative hypotheses to Omid being upset with you. If the hypotheses that we list out at the end of this process are actually exhaustive of all the ways that we could get our evidence E, Omid having made a face at us, which they typically won't be, because there will be different factors that could have led to Omid making the face that we haven't thought of. But if they were indeed exhaustive, then we would have the logical equivalence of our evidence that Omid made a face with Omid made a face and the first hypothesis was true, or Omid made a face and the second hypothesis was true, and so on. Then by our normal probability rules, in particular that the probability of logically equivalent propositions is the same, we can observe that the probability that Omid made a face at us is equal to the probability of that disjunction. For simplicity, now let us assume that our hypotheses are mutually exclusive, so they're not simultaneously true. This is indeed a simplifying assumption. This would lead to being able to apply finite additivity and getting that the probability of that disjunct is equal to the sum of its parts. From this, we apply the definition of conditional probability to unpack all the ways that we could have gotten our evidence. This now is the term we'll consider. Again, for simplicity, let's say that each hypothesis makes the evidence equally likely, whatever that value is. Let's say if Omid was upset with us, there's a half chance that he would make such a face, and if he was having a hard day, there's a half chance he would make such a face, and so on. Now we need our prior probabilities of our first through fourth hypotheses, of each of our hypotheses. Let's say that Omid relatively rarely gets upset. Maybe he gets upset something like, a dozen times a year, which would lead on any given day to a 4% chance of him being upset. Indeed, we would need it to be upset not just generally, but upset with us. And we might think it on reflection that there's an 80 out of 100 chance that Omid was having a bad day, as there are many things that can cause us to have bad days, and they're not uncommon. And we could think that there's a 16% chance that Omid was deep in thought, and a 2% chance that Omid was in distress. Notice that these need to sum to 1. If indeed these probabilities are exhaustive, they should cover the space of ways that Omid could possibly end up making that face. This is already beginning to constrain our confidence in our hypothesis, in the first thing that came to mind for us. Moreover, we can plug these into Bayes' rule. And since we had, for simplicity, let all the hypotheses make the evidence of Omid producing such a face equally likely, then all of the likelihoods cancel out and leave a reduced expression, which, when we look at it, we see gives us that there is just the 4% chance that we had that Omid was indeed upset with us. Here, because of the equal likelihoods, the posterior probabilities are the same as the prior probabilities, because in a sense, the evidence was equiprobable under any of the hypotheses. It did not discriminate between them. So we have our posterior probabilities on Omid being upset with us as 4%, Omid having a bad day as 80%, being deep in thought as 16%, and being in distress as 2%, as before. The moral of this exercise is that merely recognizing the existence of alternative hypotheses and the fact that we must distribute our credences over all of them can give us a better idea of just how confident we should be in our first hypothesis. Typically, we'll be less confident than before we had done this exercise. Now let's consider the profound value of looking for disconfirming rather than confirming evidence. In science, it's often said that we try to falsify our hypotheses. We can use probability or inductive logic to make this precise. Under this approach, we aim to find predictions, E, that we derive from our theory, H, so that the likelihood of these predictions being true, or the evidence compatible with these predictions being true, given our hypothesis, is high. But these predictions themselves are unlikely to be true otherwise, so the probability of E is low. Tests of such predictions are the most likely to show that our theory is false, and so that our posterior probability, given that the prediction turned out to be false, is low. To state this precisely, let a theory H predict event E, so that the likelihood of E given H is high. Conversely, the likelihood of not E given H is low. This is just what it means for our theory H to predict E. It makes E very likely and E very unlikely. But E itself is unconditionally unlikely. This is a very unusual prediction. So the probability of E is low, and conversely, the probability of not E is high, since the sum of those two probabilities must be 1. Imagine that prediction E turns out to be false, so that when we go to test whether the prediction obtains, we find that not E is true. Now consider Bayes' rule, which tells us in the familiar way that our posterior probability in the hypothesis, given some evidence, is equal to the product of the likelihood of that evidence and the prior probability of the hypothesis over the probability of that evidence. Only now our evidence is that the prediction turned out to be false. Whatever our prior on the hypothesis, P of H, was, we know that the greatest decrease in the probability of H, that is the lowest posterior probability that we can get, is produced just when the prior is multiplied by the smallest possible number. And what multiplies the prior is the ratio of the likelihood of the false prediction given the evidence over the false prediction. Now notice that this is just what was stipulated in our scenario. The probability of the event not turning out, given that the hypothesis is true, is low. And the probability of the event not occurring, the evidence not obtaining, is high. That is, the numerator is small and the denominator is great, which is just what's needed to minimize the value of that ratio, and so to multiply our prior by the smallest possible number to produce a lower posterior probability in our hypothesis. In these sorts of situations, when we pursue and test a very surprising and unusual prediction of our hypothesis, of our theory, it's precisely here that we have the best chance of getting strong disconfirming evidence for our hypothesis. But this is only one side of the coin. Now consider what happens if our unusual and unexpected prediction turns out to be true. Look at Bayes' rule again, but now where E occurred rather than the negation of E, our prediction turned out to be true. Here we see that the greatest increase to the probability of our theory, H, is produced just when it is multiplied by the largest value. That is, when the ratio of the likelihood of the evidence given the hypothesis over the probability of the evidence is largest. But this is also what is said in the conditions for our scenario. The likelihood of the evidence given the hypothesis is high because it was a prediction of our hypothesis, however unexpected. And the probability of our event or evidence is low because, as we said, this was an unusual and unexpected prediction. So we have a large numerator for our ratio and a small denominator for our ratio, multiplying our prior to produce our posterior. This produces the largest increase of our posterior probability on the hypothesis. The same test that has the potential to most strongly disconfirm our theory, the test of an unexpected and improbable prediction, has the strongest potential to confirm our hypothesis. Let's consider a historical example of this principle, that of the prediction of the deflection of starlight by general relativity. General relativity predicts that, due to the warping of space-time, light waves will be deflected when they pass near massive bodies, such as the Sun. In 1929, this was tested with photographs during the eclipse. The prediction of the theory was that starlight just grazing the Sun's surface should be deflected by an angle of 1.75 arcseconds, as shown in the diagram below. Here, our hypothesis is the theory of general relativity, and the event it predicts is that starlight grazing the Sun will be deflected by precisely 1.75 arcseconds. This value was predicted by the theory, so that the probability of this event was high, and the specific angle of deflection was unlikely otherwise. So the probability of this evidence, in all the cases where general relativity was not true, was astoundingly low. Think of how many values that one could receive for deflection or non-deflection of light that would not be precisely 1.75 arcseconds. Hence, this was strong evidence for general relativity, because the probability of the evidence given the hypothesis was high, and the probability of the evidence was low otherwise. And so, upon observing this evidence, one should certainly have taken it as strongly confirming of our hypothesis, and increased her probability in the truth of general relativity. Our next bias is that of base rate neglect. You've already been exposed to this bias, but now we'll consider several forms of it. Base rate neglect is the tendency, when presented with relevant base rate information, that is, general information on prevalence, and specific information, information pertaining only to a specific case, to ignore the base rate in favor of the individuating information, rather than correctly combining the two. Recall our medical test example from the lecture on Bayes' rule. When presented with the relevant information, that of a positive test result on a 90% accurate test for a disease with a prevalence of 10%, medical students and others responded that it is 90% likely that the patient has the disease. You might recall, or might be able now to quickly calculate, that the correct probability of the patient having the disease was 50%. What those responding to this information did was to simply look at the evidence of the test result, which is 90% accurate, and assume that the patient had a 90% chance of having the disease, and ignore the important background information that informed the prior, namely the prevalence of 10% of the disease. They failed to combine the information appropriately. This is base rate neglect. The corrective for base rate neglect is merely to remember the role of the prior as given in Bayes' rule. That is, don't just think about how likely the evidence is given a hypothesis. For example, the disease making a positive test result very likely. But also think about the prior probability of your hypothesis. For example, the disease being very rare. The outside view involves stepping back and recognizing the importance and the role of the prior. Often, the base rate is our best initial forecast for an event. For example, consider the hypothesis that I'll finish some project on time. We tend in such situations to engage in overly optimistic thinking about the timeline, and there's much research on how we do this. However, it can be a very valuable corrective to step back, to take the outside view, and to ask, in the past, how often have I finished similar projects on time? This should be my base rate. And perhaps I combine it with specific situational evidence, like maybe I have a lot of coffee to work with, so I think I'll do a little bit above average. Or I don't have any coffee, so maybe I'll do a little worse than average. Importantly, I will begin with the estimate that is derived from how I performed in the past. Or I might consider the hypothesis that a stock will close up at the end of the day. My first estimate should often be, in the past year, for example, how often has that stock closed up? Or take the hypothesis that the incumbent will win re-election. I might ask, in the past several years, how often have incumbents in similar situations won re-elections, and use that as my prior probability. In each of these cases, I can add in the specific individuating evidence for the situation. Maybe this incumbent is particularly charismatic, or is dealing with an economic recession, and these might shift my probabilities one way or the other. But my initial estimate will be informed by the appropriate class of similar events that will compose my base rate or prior. That said, it's often quite challenging, though important, to determine the right prior or base rate. Consider the incumbent will win re-election example. We suggested considering in the past several years how often the incumbent won re-election as our prior. But which sorts of incumbents should we count to see their frequency of winning re-election? Representatives, senators, presidents? Most likely we should pick the sorts of incumbents that are most similar to the one whose re-election prospects we want to predict. But what time frame is another question we might ask. Should it be in the past year, past 5 years, 10, 20, or 50 years? This is a bit of a harder question, because as we go further back in the past, the rate of re-election might be less relevant to the current rate of re-election. It might be less informative. if the situation has changed substantially. And which re-elections should we consider? For local, regional, national, or international re-elections? Typically, a more specific prior means less data, but more relevant data. And there's a trade-off here that one must learn to navigate, though there are often no simple answers. Our final bias is the conjunction fallacy. The conjunction fallacy occurs when one attributes greater plausibility to a more complex proposition than to a simpler one, when the more complex proposition cannot have greater plausibility. I'd note that this typically occurs because of coherence bias. This is the psychological tendency that leads us to feel that stories with more interconnections, those that are more coherent, are more plausible than ones with fewer interconnections. The famous example used to illustrate this bias is the Linda problem, in which we are presented with the following information. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. We are asked which is more probable, that Linda is a bank teller, or that Linda is a bank teller and is active in the feminist movement. Take a moment to consider which your intuition tells you is more probable. The answer is that the hypothesis that Linda is a bank teller is almost surely more probable, or at least logically cannot be less probable than the hypothesis that Linda is a bank teller and active in the feminist movement. To see what is so, consider the set of all bank tellers. Now consider the set of bank tellers that are also active in the feminist movement. The latter must be a subset of all bank tellers, and hence the probability of being a bank teller must be at least as great as the probability of being a bank teller and anything else, including being active in the feminist movement. More generally, for any proposition, conjoining it to another produces a proposition that is at most as probable as the original proposition. The Linda problem has been tested in many different ways in order to find out what exactly is driving it. What seems to be the case is that stories in general that are more interconnected, right? The initial information we got about Linda was about her concern over activist causes. And the hypothesis, the more complex one that we were exposed to, said that she was also involved in the feminist movement. There was a coherence there between the different parts of the story. And this seems to be what drives our intuitive judgments of the probability of even complex propositions. To correct for this, we need to be aware of the logical complexity of propositions as it affects their probability. If you hear a story, hypothesis, or argument composed of many conjunctions, and, you should not be thinking the story is so coherent and therefore plausible or swept away in its plausibility. Rather, you should be thinking that the probability that at least one of the key propositions involved is false is increasing with each conjunction. Indeed, we can rank order the probability of propositions, even when we don't know their individual probabilities, by their logical structure. Remembering that the probability of a tautology is 1 and a contradiction is 0. We can start with any proposition P that has some probability from 0 to 1, and notice that as we conjoin it with further propositions, its probability in general will tend to decrease. If we consider P and Q, it will be at most as probable as P. If we consider P and Q and R, it will again be at most as probable as P and Q. And we can repeat this process. In the other direction, we can also notice that disjunctions make propositions more probable. So if we take P and say P or Q, it will be that P or Q will be at least as probable as P, and P or Q or R will be at least as probable as P or Q. You can think of that in terms of a concrete interpretation as saying that Linda was a bank teller or active in the feminist movement, or above 5 foot. It makes weaker and weaker claims, because if any of those is true, the hypothesis ends up being true. This is to say, it's important to be aware of the relationship of logical structure and probability, and to avoid the cognitive bias of how interconnected storytelling can make us mistakenly feel more confident in those stories. This also highlights that there is an essential tension between what makes stories believable for us and what makes them objectively more likely to be true. This is a deep challenge to us in our prediction and forecasting, this tendency of the mind. Political and economic punditry has historically been optimized for just this sort of coherence rather than for prediction. You'll notice that many of the theories about how the world works that you'll be presented with will be extraordinarily elaborate, and they'll be using how the pieces fit in together to make them seem likely. But in fact, as they grow in complexity and claim more and more and more, we should become increasingly skeptical of the likelihood of them being true. That said, there are now starting to be exceptions to this trend, to this historical disposition toward optimizing our analysis for the biases of believability rather than the logic of probability. And just two of those that I would highlight are the Good Judgment Project and 538, which I'd invite you to look up on your own. In summary, we've covered the principle of conservation of evidence, which demonstrates for us how it is that evidence must be able to cut both ways. In particular, if observing some evidence increases our probability of a hypothesis, then observing the negation of that evidence must decrease our probability in the hypothesis. And that the more probable the confirming evidence, the more severely its negation must decrease the probability of our hypothesis. And we're exposed to 4 key biases in inductive reasoning: the availability heuristic and confirmation bias, which gave us a dynamic by which we go from confusion to certainty far too quickly. Our corrective for these was making clear predictions. articulating many hypotheses and looking for disconfirming evidence. We were exposed to base rate neglect, in which we forget the importance of the prior or base rate in learning from evidence. Our correction was balancing the inside and outside views and looking to Bayes' rule for guidance. And finally, we were exposed to the conjunction fallacy, in which we mistake a coherent story for a plausible one, with the corrective being that we attend to the logical structure of hypotheses and its effect on their probability. Be well, take good care of yourselves, and I'll see you next time.